Okay, here we go on our third lesson on powers and roots for Math 053 students. This will wrap up the rest of the chapter, chapter 5. So the final two sections, 5.4 and 5.5. Again, it does have a lot in it here, and it's just an overview, right? So we're showing you all the key ideas and concepts that come up in the chapter, but once you start mixing those all together in different ways, you really need to be doing the practice to make sure you are able to apply those ideas in different situations. For Math 052 and 038, again, the first little bit of this lesson will be useful. For 052, both in chapters 4 and 5, you will run into some situations where you have to be able to take square roots and understand what they mean. For Math 038, there is a section there, B7 Learning Task 2, where you do some basic square root stuff. I will say for 052 and 038, I will say when in the lesson. You don't really need to watch anymore unless you're interested and want to. Then, of course, you're welcome to. So what is a square root? Well, we know that when we multiply a number by itself, we write it with a power of 2, which we call squared. So like there we have 5 to the power of 2. And we know that what that means is not 5 times 2, but it means 5 times itself 2 times, 5 times 5, which is 25. And remember, we say 5 to the power of 2, or for the power of 2, we also have another way. We will say 5 squared. We'll use that language for a power of 2 because it's a special one. A square root, the way you can think of a square root is it is the opposite of squaring something. So when we say, what is the square root of 25, we are looking for the number that you multiply by itself to get 25. And obviously, we just talked about this up above because that number is 5, right? So we would say the square root of 25 is 5. Why? Because 5 is the number that you multiply by itself to get 25. We use that symbol right there, which you've probably seen before, to represent a square root. And so if we were asked to evaluate the square root of 25, we would say that is equal to 5, right? So notice I don't write the root anymore over here once I've evaluated it. The square root of 25 is the number 5, which you multiply by itself to get 25. So there also are cube roots and fourth roots and fifth roots and on and on and on. In this class, we only have square roots, but you will certainly run into the others if you have to keep on doing more math, depending on, well, you know what, any of the 07 level maths run into the other levels of roots at some point or other. So you'll probably see them. It's going to be very helpful for you, and this won't become obvious until a little later in the lesson, to become really familiar with those numbers. The perfect squares, so 2 squared is 4, 3 squared is 9, 4 squared is 16, and so on and so on. Remember, these are each just the number times itself, right? 7 squared is 7 times 7, which is 49. You might write those even as a list because there's going to be questions where you need to look for those numbers in particular in a certain context. Another thing, though, you might do is if you have a formula sheet, you might notice that this is just the diagonal down your formula sheet. So the diagonal of your times table has all of those perfect squares, and many of them have them shaded like we do here, so they're easy to pick out. So let's evaluate some basic square roots here. The square root of 16, we are looking for the number that multiplies by itself to get 16, and that number is 4. So that's the question you are going to ask yourself whenever you are asked to evaluate a square root. What number times itself gives you 81? And again, the times table sheet diagonal, you can just go right down there and find that pretty quick and find that it is 9. 9 times 9 is 81. So the square root of 81 is 9. What about the square root of 20? What number times itself equals 20? Well, okay, that's not one that's on the diagonal on our times table sheet. There is not a whole number that multiplies by itself to give 20. So there's a couple options you will have when you have the square root of a number that is not, we call them perfect squares, right? So 20 is not a perfect square, unlike 25 is a perfect square because 5 times 5 is 25. 36 is a perfect square because 6 times 6 is 36. 20 is not a perfect square. And in those situations, depending on the instructions of the question, you have one of three things you can do. The first one we don't do very often, but you will be asked to do it right at the start, is we could estimate it. So you might say to yourself, well, I know 5 times 5 is 25, which is bigger than 20, and 4 times 4 is 16, which is smaller than 20. So I know that the square root of 20 is somewhere in between 4 and 5. What exactly it is, not sure, and that's a math way of saying this. 4 is smaller than the square root of 20, which is smaller than 5, right? So the square root of 20 is in between 4 and 5 is what that says. So that's one option, estimate. So again, you'll be asked to do this in the early going in your chapter, but it's really not our main way of considering square roots. That is going to be one of the second two options. So approximating a square root. For this, we pick up our calculator and we find that square root button and we type in, depending on your calculator, you'll either type in the root button and then 20, press equals, or 20 and then the root button. There's two different types of calculators which operate in the opposite direction for functions like square roots and other ones as well you'll get into later. So if you do that, figure out which way your calculator works, you should end up with the number 4.472135595, and so on, and so on, and so on, which, as we expected, is bigger than 4 and smaller than 5, right? So if you take this number and multiply it by itself, you will get 20, or very, very close to 20, because no matter what you do, you have to stop typing in numbers eventually, even though this goes on forever. You remember we called those irrational numbers. They go on forever and ever and ever. They don't terminate. They don't repeat. That's why we call this approximating, by the way. No matter how many decimal points you take, you round it off to 2 decimal places or 10 decimal places or 100. It doesn't matter how many you take. When you take your rounded number and multiply it by yourself, you'll get very, very close to 20. So this number is very, very close to the square root of 20. And in fact, you'll find that we start to use language in math like this, where the root 20, shown like this, we call an exact number. And this, when we start writing out decimal places, is always an approximation of that exact number. That throws some students because they look at this, this root 20 looks like nothing. We didn't even do anything. But that is the exact value of the square root of 20. We just haven't written out any of what the decimal points are. This over here to students looks a lot more like an answer, and yet this is just an approximation because, again, no matter how many decimal points you decide to keep, you haven't kept all of them, right? Even if you keep 1,000 decimal points and write them all out, you still have to stop at some point. So that is just the approximate value of the square root of 20. This third one over here, simplifying, we're not going to do right now. We will come to that later in the lesson. That's actually probably the one you will, in Math 053 students, you will run into most often. Math 052 and 038 students, you will pretty well always simply be approximating, typing these into your calculator and getting an approximate value. Okay, so when you have a square root, it is the same thing as a bracket in terms of order of operations. In other words, BEDMAS, brackets are first. You got to work out whatever's inside that root first. So if you have the square root of 9 plus 16, like we have there, we have to work out the inside of the root first, 9 plus 16, which is 25. Then we can apply the square root. What times itself equals 25? 5 is the answer. Notice, you cannot do this. You can't say, oh, hey, square root of 9 is 3 and the square root of 16 is 4. So I just add those up, and then you see you get the wrong answer. You get 7 instead of 5. So you cannot, when there's addition inside this square root sign, you can't you can't take the root of the separate things separately. Here we got another one here. I'm going to give you a minute to try on your own. Follow order of operations inside that root and then evaluate the root. Okay, so we look inside that root, which we know we have to work all this out first. And we see we have bed mass, order of operations. We want to do this multiplication here before we do the subtraction. So 3 times 7 is 21. Now we can subtract. 142 minus 21 is 121. And now we ask ourselves the question, what times itself equals 121? Again, check down the diagonal of your times table sheet to see if it's there. Sure enough, it is. 11 times 11 is 121. So the square root of 121 is 11. All right, here's another one. So we got, you see, getting a little more complicated there, but we still just got to go a little bit at a time. What we want to know here is that when you see something like this, with a 3 written in front of the 49 there, the root 49, that is actually multiplication. Once again, mathematicians just love to be lazy. If they can get away with it and say, hey, how about we don't put the times sign in there and everyone just agrees that we know it's times, they'll do it if they can, right? So what 3 root 49 actually means, you want to always remember, is 3 times root 49. Now, I wouldn't bother writing it out every time, but maybe at the beginning you might until you get used to it. So what this actually says is 3 times the square root of 49 minus 2 times the square root of 29 plus 7. All right, let's think through our order of operations. Are there any brackets? Yes, there are, because the square root acts like a bracket. So we need to work out that 29 plus 7 first, and I'm going to let you take a minute and give that a try, see how you go at it. Okay, so we're going to work out under that root first because it's the equivalent of a bracket, 29 plus 7, which is 36. And now let's see, we got some multiplication and subtraction. We know order of operations. We've got to do the multiplication first. Of course, we can't. In fact, you could still think of these roots as being like brackets, right? We can't go 3 times the square root of 49 because we first need to know what the square root of 49 is. So in both of those, we continue to work out that bracket essentially. Square root of 49 is 7. Square root of 36 is 6. Because 7 times 7 is 49 and 6 times 6 is 36. Now we got multiplication to do first. 3 times 7 is 21 and 2 times 6 is 12. Now finally we get to the subtraction. 21 minus 12 is 9. Roots and negatives. Okay, well here's another one to evaluate. What is the square root of negative 9? And remember, to do this, we ask ourselves the question, what times itself is equal to negative 9? Well, we know that 3 times 3 is positive 9, so that's not it. And so a lot of students will think, well, it must be negative 3. But think about it. What's negative 3 times negative 3? Negative times a negative is a positive, so negative 3 times negative 3 is also not it. You think to yourself, well, 3 times negative 3 is negative 9. Sure it is, but that isn't something times itself, right? So what we discover is there is no real number that multiplies by itself to give negative 9. Now that might sound funny that I said the word real in there. Why not just say there is no number that multiplies by itself to give negative 9? Well, you will discover in your future math courses, depending which ones you take, I guess, that there is something that we call, well, they were originally called imaginary numbers. We like to try to call them complex numbers now because it turns out they're not so imaginary when you, because they actually turn out to have real world implications if you do physics questions and you get so-called imaginary numbers, but you continue to work through to the end, it turns out you get a answer that is legitimate in the real world and matches experimental results, which is a bit crazy, but none of that is required for math, any of the maths that you're in. Just something kind of interesting to know about. So we say there is no real number, or we might say that the square root of negative 9 is not a real number, right? We can't do it when we're just talking about the real numbers that you guys know of when we think of our number line. Contrast that with this situation, which again, we ran into this with absolute values too in the review chapter, but this throws people because this one over here is the square root of negative 9. There is no number that does that. This is the square root of 9, but with a negative sign in front of it. That's not a problem. Let's separate those out. We got the negative sign in front in red, and then we have in blue the square root of 9. Well, let's just look at the blue. What is the square root of 9? It's 3. The negative sign is still out front, and then there's a 3 there. And that is our answer. So, again, if you think, but wait, I thought it couldn't be negative. Well, it wasn't. Look at the square root of 9, right? The square root was not negative. Look at the blue. The square root of 9 was positive 3. But then in front of that positive 3, there was already a negative sitting there, which can't magically go away, right? It's got to stay there. So to summarize that, the square root of a negative can't be done. It's not a real number. But having a negative in front of a square root is no problem at all. Okay, the product of two roots is the root of the product, and the same for quotients. That's not nearly as confusing as it sounds. That means if we are multiplying two roots like this, right, no addition or subtraction there, just straight multiplication, the root of 6 times the root of 24 is the same as the root of 6 times 24. This might not seem all that useful until you watch what happens next, because if we had tried to evaluate the root of 6, we can't. We'd have to type in and get a decimal answer, or just leave it as root 6, an exact answer. Same with the root 24, there's not a number that multiplies by itself to get 24. But when you multiply 6 times 24, and obviously I picked one here that works nicely, what times itself is 144? Go down the diagonal on your times table. That one does exist. It's a nice number, 12. Give this one a try. I'll give you a minute. Okay, so the square root of 72 divided by the square root of 2. I have just told you that. That we can rewrite that as the square root of 72 over 2. What is 72 divided by 2? It is 36. Is that a nice perfect square? So can we actually evaluate it as a nice number? Yes, we can. The square root of 36 is exactly 6, because 6 times 6 is 36. Okay, Math 038 and 052, you're off the hook. If you want to stick around and watch the rest, you are welcome to, but that is about the extent of what you're going to run into. You're going to run into questions where you have to take a square root at the end of a question, often when you're working with a formula, in order to get the answer you need. And often it is going to be a decimal approximation, because when we're working with real world situations, even though it's only an approximation, we usually do want that decimal number, when we're calculating, a length on a construction site, or the volume of a container, or those types of situations. All right, moving on specifically for the Math 053 students. Now we're going to throw some variables in there inside of our roots. So I'm going to ask you what is the square root of a to the power of 10? And so remember, what we're asking ourselves is what times itself is equal to a to the power of 10. And you might initially be tempted to think, well, nothing, because 10 isn't a perfect square. But take a look. What is a to the 5 times a to the 5? What do you do when we multiply with the same base? What do we do to the exponents? That's right, we add them. And what is 5 plus 5? It is 10. So actually, there is something that multiplies by itself to give a to the power of 10. That something is a to the power of 5. When you multiply a to the power of 5 by itself, it becomes a to the power of 10. So therefore, the square root of a to the 10, it actually is a perfect square, and its square root is a to the power of 5. And that will be true if you think about it for any even number, right? The square root of x to the power of 40 is going to be x to the power of 20, because x to the 20 times x to the 20, you add the exponents and get 40. Okay, the square root of m to the power of 16. I purposely picked one that tricks people here. What, you ask yourself the question, always, every time, right? What times itself is m to the power of 16? And the answer is m to the power of 8. Because when you multiply m to the power of 8 times itself, we know you add the exponents, and that gives you 16. Notice it is not m to the power of 4, right? Some people will do that because they think, oh yeah, 16 is a perfect square. 4 times 4 is 16. Yeah, it's true. 4 times 4 is 16, but this is not 16. This is m to the power of 16. M to the power of 4 times m to the power of 4 is m to the power of 8, not m to the power of 16. And this last one over here, well, that's an odd number. So a to the power of 25 is not a perfect square. We can't just get rid of that root sign like we could for these two over here, but we will later on in the lesson learn what we can do to partially simplify that. Okay, we can put a bunch of stuff in the same root. So here we got the square root of 64 times h to the 14 times p to the 4. What we saw earlier is that if two roots are multiplied, we can combine them together inside the root. So we can take that same idea and just do it backwards. So this will be the same as the square root of 64 times the square root of h to the 14 times the square root of p to the 4. And these are all perfect squares because what times itself gives 64? 8 times 8 is 64. What times itself gives h to the 14? H to the 7 times h to the 7 gives h to the 14 because you add the exponents. And what times itself gives p to the 4? P squared times p squared gives p to the 4. Now I did that last one on purpose. I want you to think about that. Why is p squared the square root of p to the 4? Not because the square root of 4 happens to be 2. That's just a fluke. The square root of p to the 4th is p squared because when you multiply p squared by itself, you add the exponents and get p to the 4, right? That's why the square root of p to the 4th is p squared. So there's our answer. Put it all together, 8 h to the 7 p squared. I think most of you can see you could probably skip both of these steps, right? You just look at all these things being multiplied. Notice this is different than earlier on. We had things that were being added or subtracted under the root, and we could not do them separately. But if they're all being multiplied, we can break them out. So you could just jump straight from what is the square root of each of those things and write your answer, I think, once you get the hang of this. Okay. Finally, we're going to come back to those weird ones that aren't perfect squares. And in fact, that's the vast majority of numbers in the universe, such as 20, right? Only a very few are perfect squares. What we're going to find is that even though we can't evaluate that as a nice integer number, nice whole number, we can break it down. So what we notice is that we could break 20 if we wanted to into 4 times 5. Like so. We already know we can split those apart. So the square root of 4 times 5 is the root of 4 times the root of 5. The root of 5, well, we're stuck, right? That is still not a perfect square. We can't do anything with that. It stays inside the root. But the square root of 4, we can do that one. 2 times 2 is 4. And remember that we usually don't bother to write that times sign there because we're lazy. So your answer, 2 root 5. Again, you'll get good at this. At the start, I would suggest breaking them apart. Follow this example that we just did. Break it apart. Evaluate the one that can, and then it becomes pretty obvious, right? There's the root 4 that you're able to evaluate is out front, no longer in a root. The root 5 is stuck behind. You can't get it out. Now, why did that work? That worked because 20 happened to divide evenly by one of our perfect squares, 4. If that hadn't happened, then we wouldn't have been able to do this. Also notice that if we had broken 20 into 10 times 2, that wouldn't have helped at all either, because root 10 isn't a perfect square, and 2 isn't a perfect square. So you're not just picking any two numbers to break 20 into. You are very specifically looking for perfect squares. I do have students sometimes who they all get it eventually. Don't worry, but they'll come up to me like over and over and over the first day they learn this and say, "Why isn't this working?" And they've broken, 40 into 8 times 5. Well, 8 isn't a perfect square and 5 isn't a perfect square, so that's not going to help you, right? You need those perfect squares. There they are again on the right. Either list them on your cheat sheet or have a times table sheet with you, and remember that they're down the diagonal. So let's try a few of these here. So here's what we're looking for. We're going to look at that 75, and we're going to try and find one of our perfect squares that goes into it evenly. Let me give you a suggestion here, something I see students do. Don't just sit there and stare at 75 and await inspiration from on high about what number to divide out. Go over to your list, which you've written down or have on your times table sheet, and just start trying them. Does 75 divide by 4? No, and in fact, we can just skip all the evens because there's no way 75 will divide by an even number. Does 75 divide by 9? Check your times table sheet or try it on your calculator or know your times tables, any one of those options. No, it doesn't divide by 9. Skip 16. Does 75 divide by 25? Oh, yeah, it does. 75 can be broken into, yeah, there we go. 25 does. 75 can be broken into 25 times 3. I picked a perfect square, right? You may or may not know that 75 can also be broken into 5 times 15, but that doesn't help us because neither one of those is a perfect square, right? So find a perfect square that divides evenly. Now we know those can separate out. The square root of 25 is 5, and the square root of 3, well, that one just stays. We can't do anything with that, like so. Why don't you give those two a try on your own? Give you, 1 or 2 minutes. Okay, does anything from our list divide evenly into 45? And you'll find, again, that you can, just by quickly trying these, either on your times table or if they're bigger numbers, just picking up your calculator. It doesn't take long usually to find one that divides in. So 4 doesn't divide into 45. Does 9 divide into 45? Oh, yeah, it does. 9 goes into 45 evenly, so let's break 45 into 9 times 5. And I will point out once again, 45 we could have also broken into 15 times 3, but that wouldn't help us, right? We need a perfect square because we separate those out now, root of 9 and root of 5. The square root of 9 is just 3, and the square root of 5 is left behind. There's our answer. Now this third one, I'm going to guess that some of you might have tried it and got part way, but not all the way. So let's take a look at this one. Do any of our numbers divide into 108? You might have caught right away, in fact, it's very likely you would, that 4 does go evenly into 108. Ah, perfect, you say. So 108 divided by 4 on your calculator, you get 27. So 108 breaks into 4 times 27. The root of 4, notice I'm starting to skip a step there. I'm skipping the step where we separate them out like this. But you could if you want. This breaks into root 4 times root 27, and the square root of 4 is 2. And you think you're done, but hopefully you now notice that, wait a minute, no, we're not done. This is just like reducing fractions. You got to check to make sure you got it all the way down, because 9 goes into 27. So we break apart that 27 now into 9 times 3, because 9 is also a perfect square. What's the square root of 9? It is 3. And notice I've reminded you that this 2 root 27 is a multiplication sign. Otherwise, people forget. They're like, what do I do with the 3 now? Well, remember, this actually says 2 times the root of 9 times 3. So this is 2 times 3, the root of 9, times the root 3 that's left behind, right? Because you can't get that one out. So 2 times 3, we get 6. And I feel like that might be down at the bottom out of the view for the people watching the recording later because of the toolbar. I apologize. The answer is 6 times the square root of 3, 6 root 3. Now, we did that by first pulling out a 4 and then pulling out a 9. If we had really been on the ball, we might have instead noticed that actually 36, another one of our perfect squares, goes into 108. And if we'd noticed that, we would get to the answer a lot faster. 108 is 36 times 3. And again, you just use your calculator for that. 108 divided by 36 equals 3. There you go. It's broken apart. Separate them apart if you want to show that step. Root 36 is 6. And the root 3, can't do anything with it. And we notice that we get the same answer either way. We get 6 root 3. So what do we learn from this? If you can find the biggest perfect square that goes into it, great. You'll save yourself some time. Is it worth spending an extra 10 minutes trying to find that biggest perfect square, which may or may not even be there, right? You might already have it. I don't know that it is. There's nothing wrong with breaking out the 4 and then double checking to see if there's anything else that continues to break out. Okay, so here we're reducing, this is called, or simplifying roots, and these ones all had numbers. We can do the same thing if there are roots of powers. Remember, we are no longer looking for our list of perfect squares, right? Because x to the 25 is not a perfect square, even though 25 is. We are looking for even powers. So when we have a to the 25, what is the biggest even power that we can break out? It's a to the 24. We can break a to the 25 into a to the 24 times a to the 1 because we add those exponents. And again, if you're sitting there thinking, why isn't the answer a to the 5? Remind yourself, what is a to the 5 times a to the 5? It is a to the 10. You add the exponents. It is not a to the 25, right? Now, separate those out. And that first one, you just slice that power in half every time, right? Because what is the square root of a to the 24? It's the thing you multiply by itself to get a to the 24, which is a to the 12. A to the 12 times a to the 12. You add the exponents and get 24. And that a to the 1 over there, we can't do anything with that. We normally don't bother to write a power of 1, right? If we have a to the 1, we'll just write it as a. So there's our final answer, a to the 12 times the square root of a. So yeah, give B a try. You're on your own. I'll give you a minute. Okay, so when we have numbers, we want to look for powers, or perfect squares rather, that divide evenly into them. When we have exponents, powers of variables, we simply want to take out the highest even power we possibly can. So in this case, t to the 30. T to the 30 times t to the 1 is t to the 30 plus 1, 31. The first piece there will always be a perfect square by slicing the power in half. So this reduces to t to the 15 root t. This last one over here, we can just do those two separately. We got a 63 and an x to the 13th. Let's break them both apart. For the 63, we want our list of perfect squares again, because this is just a normal number. What is a perfect square that divides into 63? Well, actually 9 does. 9 times 7 on your times table sheet if you want. 9 is the one we're looking for. 63 breaks into 9 times 7. Now for the x to the 13, we no longer want our list of perfect squares. We simply want to take out the highest even power we can, which is 12, like so. And how do I separate those all out? Nope, maybe not. So let's just jump to close to our answer. The square root of 9 is 3. The square root of x to the 12 is x to the 6. So those ones can come out front because we can actually work them out as perfect squares. And let me say one more time, look in the red, 3 times 3 is 9. Look in the blue, not 6 times 6 is 12, but x to the 6 times x to the 6 is x to the 12 because you add the exponents. And the other stuff is stuck in behind there, the 7 and the x to the power of 1, which we don't bother to write, we just write x. So there is your answer, 3x to the 6th times the square root of 7x. Okay, so that's the key ideas. I'm going to do one more example because I just want you to see, as always, you can practice each one of those ideas separately and they're fairly straightforward. But we start to put all those scenarios together and the questions can get more and more complicated. And again, we can't, in this lesson right now, we're actually over time already. We can't go through every little possible variation of questions. So you need to do the practice, understand the main key ideas, and apply them. So here we got a square root of a big fraction. And in general, when you have fractions, if you can reduce them, you want to do that first before you start doing all the other stuff. If your fraction can get smaller, that's going to make everything easier, right? So I got a 50 on the top and an 8 on the bottom. Those both divide by 2. So that starts to help. 25 over 4. In fact, you can probably see why that's very helpful already, because those are both perfect squares, whereas 50 and 8 were not. We have r to the 7 on the top and r to the 5 on the bottom. And you remember, depending how you want to think about that, you're going to end up with an r squared on the top. Either you thought 7 minus 5 is 2, and the one on the top is bigger, or you might think this is like 7 r's being multiplied on the top and 5 r's being multiplied on the bottom, so all 5 on the bottom cancel out, leaving 2 behind. Here, this is the opposite scenario. You have 11 s's multiplied on the bottom and 3 s's multiplied on the top, so 3 of the 11 on the bottom cancel out. Or you might have thought 11 minus 3 is 8, and the bigger one is on the bottom, like so. Either way, whichever way you go about that. So let's carry on now, because we have reduced the fraction, and everything here you might notice is a perfect square. 25 is a perfect square, 5 times 5. 4 is a perfect square, 2 times 2. R squared is a perfect square, r times r, or r to the 1 times r to the 1, because 1 plus 1 is 2. And s to the 8th, any even power, perfect square, because s to the 4th times s to the 4th. So let's work those out. We can separate the top and the bottom as we saw earlier. So one at a time now. The square root of 25 is 5. The square root of 4 is 2. What times itself gives r squared? R to the 1, or just r. What times itself gives s to the 8? S to the 4 times s to the 4. So there's the square root, and that is your answer. So again, the questions are going to get increasingly complex for the Math 053 students. Know the basic rules and go through the examples in the text, try the try-it questions, try the practice at the end of the section.